Good morning. We're starting on time. Last week, remember the fiasco with the cables up here being messed up, so I don't have that, fortunately, this morning. Nobody tampered with it since last week, and I was able to plug right in. So what is new for today is that I've posted up sets 5 and 6 just so that we can have the complete layout that takes us. I'm going to put up the calendar here. The complete layout that's going to take us through the Thanksgiving week and getting into that. So the assignment you're currently working on, which was, remember last week, was set number 5, or 4 I mean. I had mislabeled, never intended to have it due last Friday. It is due on this Friday, on the 4th. And then there's a short assignment that wraps up Chapter 4 with some probability, random variables and random processes stuff. That one's due on the 11th. It's short term, but there's 3 problems on it, and there's 1 bonus problem. And then the next assignment is all of Chapter 5 rolled up into a few problems. There's a possibility that I will trim some out or make some of those bonus problems. That one is due on the 18th, 1 week again. The problems will, I'll just say it this way, even though it may not appear that way. I said there's a lot of work to be done, and it's going to be painful to get through the rest of the semester for a while. But then things do start to get easier. The problems tend to get easier towards the end. And Chapter 5 is kind of the beginning of that, because it's pulling everything together and just using it in sort of nice, informative ways where you're synthesizing everything together that you've learned so far. What I'd call the DSP math is now behind us, and now you're going to use the DSP math to actually solve problems, and that's Chapter 5. What's going to happen, though, that's special in Chapter 5 is that, well, on the 18th, is I will be posting the take-home exam, which you'll work over the weekend, and you'll come back on the 22nd, not to me personally, but virtually, you will turn in that take-home exam. And then you can go spend Thanksgiving with family or wherever you might decide to go to, or if you decide to stay here and work, more power to you, because I think that's probably going to have to be done no matter where you're at, is my thinking at least. Nominally, the Project 1 is also due on at that time frame. I've occasionally extended it past Thanksgiving weekend. I don't want to make that announcement yet because I want to keep driving you to get that out of your hair. And I'm going to be talking more about it today too. And then there'll be a mad dash after that as we head down into the last 2 weeks of the semester. And what I'm talking about is it'll be the week of the 28th through the 2nd, and then the week of the 5th through the 9th of December. And that will be the last 2 chapters of material. There's a chapter on topologies, basically how we take algorithms. We've had the fundamental difference equation for a long time now, but how you can build different architectures to implement things, and structure, signal flow graphs, and a little bit of quantization theory gets woven into that as well, because topologies do change how fixed point arithmetic operates on signals. And then the last chapter is a combination of chapters from the book, but it's the FFT chapter, the one that I decided to put in its original place from 2 years ago. And then, of course, the other thing that will happen when we come back from Thanksgiving is I will formally have on deck the project. So I'll probably be posting that or reposting it during Thanksgiving week. But remember, that project is going to be the GPS acquisition and tracking project. The old version of the project is up there. I'm probably not going to change it very much. It's totally canned. The software is all canned up. You just have to learn a little bit about the application and how DSP can be used to process signal is picked up by a GPS receiver. It'll, of necessity, be a complex baseband signal, so it'll be a complex signal as if it's coming from the satellite. The only thing I don't have modeled in this is Doppler, which is definitely present in GPS signals because those satellites are in medium Earth orbit. They're moving, so that means there's a Doppler on them, and it changes with their position somewhat. But you still get to play with it in a fair amount of detail and learn a little bit about spread spectrum communications and also, again, how GPS works. The thing that you calculate in that project will be what's called the pseudo range, and the pseudo range is used in a algorithm, a least squares or Kalman filter, and I have that hosted on a GitHub site, a Kalman filter approach to it, to process the pseudo ranges, use the ephemeris data from the satellites that you're tracking, and then come up with what? What's the thing that we always use our GPSs for? Get our position, right? So I can show you a project that uses a Kalman filter that goes and takes the pseudo ranges and converts them into actual coordinates on the Earth. But then you'll also get introduced to different coordinate frames too. That's kind of a topic unto itself. I like to use east, north, up, or ENU is what it's called. So east, if my right side was the east, which actually it's that way, but just pretend it's to the east. North would be facing that direction, right? If that was east, north would be that direction. And if you cross, think of your right-hand rule. Does everybody remember the right-hand rule? It's very important here. Cross your east and your north, and where does your thumb point? Up. So that's your third coordinate in the ENU system, which is good for local coordinates and mapping over terrain and stuff. I'll get more into that later, but maybe I'm trying to excite you. I don't know. Everything to me is exciting, but I know sometimes it takes getting into stuff. If you're a backpacker or virtually anything outdoors and you rely on your GPS, it's kind of interesting and exciting to understand how it actually can do those things for us. And what would happen if it breaks, and it could break, right? The Russians have said they would shoot down GPS satellites. They have their own system for navigation. I guess we could retaliate and shoot down their satellites or something. I mean, everybody in the world, though, uses our GPS satellites, I believe. That's true, isn't it, Caleb? And we can turn it off, too, if we want to. We can turn off we can turn back on selective availability, which puts a dithering signal on the course acquisition code, which degrades its performance the way we've used it. And not a trick question, a history question is what president turned off selective availability for the whole world? Yeah. Does everybody remember Bill Clinton as a president that we had at one time? Or vaguely, maybe? It was a really big deal. That was when GPS turned into quite the global thing, because with the selective availability turned off, which jitters the signal on purpose, then you can't get as accurate of position fixes as you can with it off. But we can turn it back on again, the selective availability, at any time we want to. And then the precision code, or P code, and Y code, and the other things are used by our military to get really precise things. And I'm guessing Russia probably has the same thing with their GLONASS system, and I think China has a system. What other government has a system right now?
There's the Galileo system. It's the European Space Agency.
Okay, that's right. At any rate, I got a bit sidetracked, but see, I wander on things because what do you do when you go work on a job? You're going to be working on all these different things, and they're going to different systems that we fielded that have used the fundamentals here are factor into the projects that you work on. Okay, so I talked about set 5 and 6 up there. I'll probably get the hints posted soon for set number 5. I do want you to finish set number 4, obviously, because that's due on Friday, and I do have that with me. And the project is like a background task that you should just be working on, and I'm going to spend some more time looking at it today. I'm actually starting, I've never done this before, but I'm thinking about putting up a comments page for that. I did some commenting last week, and I'll explain that later. Why is that even on my mind? Well, yesterday I sat at the hospital because my wife had a heart procedure. So I was sitting there in the waiting area while her procedure was going on, and I worked on this class quite a bit, and I started working on, even before yesterday in the hospital, I started working on the take-home exam. Why would I do such a thing as work on it already? Well, I'm just trying to lay things out because I'm looking at how the end is coming for me, and I've got to just kind of be prepared. So the take-home exam will have a nice comment section at the end of it that gives you hints and things when you get the problems to work. Okay, so what we want to do today is wrap up this chapter and hopefully maybe take a look at chapter 5. So we're going to be just getting into discrete time random signals and trying to see how we're going to use them. Assignment number 5 will definitely be doing some things with random signals. The take-home exam will do some more things with random signals. In the book has been doing things with probability and random signals, probability up through random signals all the way along. You just haven't probably noticed it. It starts already in chapter 2, and then it shows up in a few homework problems way at the back of each chapter from there on out pretty much. And then there's also an appendix on probability, random variables, and random processes in the book. It's Appendix A, I think. If I could trust my microphone, I don't want to risk ripping it off. I'd grab my book, but it's in there. So that's kind of my plan when I originally wrote these notes, was to say I'm not going to drill into those types of problems until I want to just sort of do the whole thing. And this is that time right now, because we're headed towards quantization from A to D's and finite bit precision, arithmetic, and also we're going to look at coefficient quantization. We've done things with filters, right, or difference equations that have the A and B coefficient vectors or arrays, right? Those are double precision the way we've been doing them, either in, if you were doing them in MATLAB and 3205, this class using Python or Julia, it's all double precision. But what do you end up doing in hardware? Very frequently the coefficients are quantized to 16-bit signed integers, or maybe even lower than that depending upon the application. If you were working in an FPGA environment, they might, in some applications, decide to use even fewer bits for the task. But 16-bit signed integers is a pretty popular fixed point word size, and that's what chapter 6, when it goes in, when we discuss topologies, then we'll be looking at finite precision arithmetic. You'll have a homework problem where you will do some quantization and just see the impacts of that. And that flashes my brain with the simple underscore spectrum analyzer. Remember from last week the problems I had with that? And then at break time I started up a different virtual environment for Python. That has been resolved and is now sitting in, I guess I should just go take a quick look at that. I'm going to be in this in momentarily when I do some Python, but I took the zip folder, put it on my desktop here, and what I've got now inside of there is simple SA underscore new, which works with Python 3.10. And that's going to get pushed in pretty quickly. Charanth, who's running the lab with me, is trying to get that pushed in to the GitHub repository, and then it will be downloadable. You'll have to go back and use Conda within your virtual environment underneath Julia, and then you'll be able to put that in. But for the rest of the semester, it's just perfectly okay to use this simple spectrum analyzer underscore new, and we'll see today how I have that folded in when I do some Python. Another thing that you need to use with the Pi Audio Helper, which I'm going to talk about some today too, is that module got messed up too. He was doing some repair work last fall and he pushed things up and he broke a bunch of stuff, which definitely didn't make me happy. I've now convinced him over the summer when we met a couple of times it's definitely broken, and I definitely have the old code that works just fine. And that's what you have in here. So you have, in this case, Pi Audio Helper underscore old. So both of those are useful for any homeworks, the project, of course. They'll be utilized in the take-home exam. So just work it that way for now. I don't know when Scikit DSP.com will have the newest versions pushed into it. So I'll show you how this works and how you fold this in Python at least. Move this back so it's ready to go. So I'm just giving you all kinds of things about random signals where it's going to get used. So there will be a simple underscore quant for quantization, and that will be a function that will take signals or coefficients in double precision, and then you can set the dynamic range on the coefficients or signal values, and then you can quantize with signed arithmetic. And it's a pretty handy little function for doing that stuff. And no, it's not something you're just going to think about using. You will be using it. I will be making you use it. So, but it's cool. It's stuff that is more contemporary than modeling everything mathematically. So probability, I don't want to spend much time here, but if you remember back to having your probability in stats class, you have an experiment which has a bunch of outcomes. I use the notation chi. Chi sub I are the outcomes that sit in the sample space, and the sample space is the script or calligraphy S. And if you take the possible outcomes and form subsets out of those outcomes, now you have what is called an event. So the subsets form events. So we might have event A is just chi1, event B is chi1, 3, and 5. And in particular, there's a lot of mathematics formality in prob and stats, if you remember. So events are sets of elementary outcomes, and you can talk about one set being a subset of another set. So that's just the math notation. A is contained in B. Formally in mathematics, subsets of the sample space. I'm now going down to the first bullet down here. See if maybe I can get my pen to work. In algebra, it's called a sigma field, and they're sets that have certain properties algebraically. That's not my strong suit by any means, but I know people just down the hall from my office that are the algebra people in the math department, and that's what they do. I'm just calling it out to say that they make up a sigma field, and if it makes up a sigma field, then certain properties will hold, and I'm just going to review what those properties are. The other two things about events is that the sample space S is called the certain event. So when you run an experiment, something always happens. So the probability associated with a sample space S is 1, because something always happens. The empty set is the impossible event, just saying that no, when you run an experiment, it's not that something doesn't happen. It does happen. It might be that what does happen has a probability of 0, and that's the abstraction of probability, right? You can declare an event like, let's just put it in a practical sense. If you play board games a lot, my family likes to play board games. We could compare notes on some of the games I bet you play in your family. Catan, does anybody play that game? How about pandemic? We started playing that one during the pandemic. That's kind of a fun game. Relates to pandemics and having to rush to the scene to put out with pandemics. The guy who created it, I'm sure, was a computer science person because it's very involved and it's very, well, the way it plays out is fairly realistic, I think. At any rate, getting back to the idea of probability and assignments of events, you can have, like when you roll a die, you can think of that as being representing a sample space of 6 possible outcomes. Does the die ever land on the corner and just stand there on its corner? Has anybody ever had that happen? I would call that the impossible event. I mean, it just never occurs, and there's no probability associated with that because it never occurs in theory. But you could rig a die, I suppose, so that rather than being smooth on the edge, it was chiseled, so when you rolled it, it might actually land there. You know, of course, all of us have heard about loaded die that favor certain dots versus other dots, and a lot of other strange theories about which side should be up based on mechanics, right? Because you've got the dimples and all that stuff. Does that change? Has anybody ever thought about that? Every face should come up equally likely, but due to mechanics, it might not because of the moment of inertia when the cube is spinning and the way the mass is distributed, not evenly because of the dimples or something. Sound crazy? That's the amazing thing about probability theory. It's got a lot of power attached to it. Okay, fundamentally though, when we associate an event with a measure, then we call that the probability, and probability of an event is always greater than or equal to 0. If it's the certain event, which always occurs, that's probability 1. And if we talk about intersecting 2 events, 2 sets now, that are mutually exclusive, in other words, their intersection contains no common points, then we can write the third axiom of probability, which relates to the unioning of 2 mutually exclusive events, and it just says that that's the sum of the 2 probabilities, and that is kind of a famous one. And then that also extends to, so make this bigger, that extends to axiom 3a, which is the infinite additivity idea that you can have a unioning of a countable infinity of mutually exclusive events, and then that will be the sum of the probabilities. This is used in what's called total probability, if you remember back to that. We also have joint probabilities, which is the intersection of events A and B, using the 3 different notations here that electrical engineers fall into. Which do you think, or which of those 3 do you like to see the best if you were working a probability problem? Just curious, tracing back in your memory, do you like to see that? Which is, I think, more like logic circuits, right, when you're ANDing things together. I think of this one as being more like what mathematicians like to use. The cap is what that's called. The cap is signifying they're intersected, whereas the cup is the opposite of that, was used up here. That's the unioning. This one, though, extends nicely to random variables. This, you just interpret that comma as saying probability of A and B when you see that comma, whereas this from logic circuits should be burned in your brain to mean and, right? I never took logic circuits though. When I was in school, I opted out of it because it wasn't something I had to take. I took other things, electromagnetics, and what else did I take that was, well, I've told you about complex variable theory. I did that. I did an advanced differential equations and some other math classes. Okay, the other thing about probabilities, we can define conditioning. So conditioning, we can say event A given B, and that's defined as the probability of the intersection divided by the probability of the conditioning event. So generally when I think about this idea, it's supposed to be a sample space. So the sample space is the entire space when you run the experiment. A and B are contained within the sample space as events. When you want to find the probability of A given B, what you're finding then is you're finding the probability of the intersection of A and B, which is the crosshatched region. And then if you're going to condition it upon event B occurring, you are effectively dividing or normalizing by the probability that B occurs. So I think of conditional probabilities, conditional random variables as just subsetting things. You're conditioning that something has already happened. Namely, in this case, if B has already happened, your scope is now gone from the sample space down to just the event B, and everything is relative to that as your new sample space. That's why you're dividing through by B, because that normalizes things back up to 1 again. Then we have Bayes' rule, which spins things around to solve for one conditioning given the other conditioning. And then coupled with that is total probability. Don't really have any specific examples for those that we're going to be using going forward. We are going to occasionally think about conditioning, but more often than not in signals and systems applications, the way the conditioning idea comes about is that we're going to be solving a problem where we have different types of signals present, different types of interference present, different levels of noise present. So we might be interested in solving for some performance given something is true, like given this jammer is turned up to this level, or the noise is at this level, or the signal is of this type, and then you solve a probability from some random variables that are in the problem. And that's two fundamental things I think about are hypothesis testing and estimation theory. So hypothesis testing is which of the conditions are true, because you don't know what the transmitter or what event is present. I'll use kind of a bizarre example, but it just popped into my head again. And since it's been in the news, North Korea is going to blow up another nuclear bomb pretty soon, is what they're saying. And that's going to create some sort of seismic activity, and we're going to be monitoring for that seismic activity. So our seismic sensors are going to detect something, and they're going to have to say what when they see that seismic activity. They're going to want to process it in such a way, but a fundamental detection theory problem would be, was it just an earthquake or was it a detonation? So those are it's a binary hypothesis problem. If you're doing radar to avoid somebody approaching you and shooting at you, you'll use a radar to detect the presence of an enemy target coming at you versus just noise in the background. So the radar would shoot out and look for a reflection, and if it gets just null, which is noise, then that hypothesis would be noise only, or it could be noise plus signal or noise plus target. So that's another hypothesis testing. The estimation theory side of things uses conditioning as well. The same ideas of conditioning, except now rather than doing a hypothesis testing, you would do estimation where you're going to try to estimate some parameter like velocity, position, temperature, those sorts of things. Both of those now, just as a sidelight, both of those ideas of hypothesis testing and estimation have morphed into machine learning and deep neural networks and everything. So if you were to dive in and read a simple article on machine learning, you'd find out that one type of machine learning is to have a big database, big data actually, and then you have some sample data and you train using the big data, and then you pass your given test data through it to see if it can discern what class or what hypothesis is present. So that's a hypothesis testing problem, and they tend to do that with training with a large data set. If it's an estimation theory problem, it might be using that same data set, but rather than just trying to detect the presence of one thing or another, it would be actually to estimate the quantity. And these are the types of things that we've been doing for a long time. Every time we have an election, we have predictions, right? They sample the population and then they form an estimate of who's going to come out on top in some race. Or I think the big one right now is control. Is it of the House or the Senate? Because I get confused by Democrats or Republicans. But that's all involves probability and hypothesis testing if it's just saying this or that, or estimation if it's trying to put a number on something. All pretty nice stuff. And machine learning is tending to be the buzzword for everything. I'm old-fashioned though. I like it, but my old-fashioned way is I have simple models. I just work with what I've got rather than having this huge amount of data stored away. But most of us know that we've been collecting data like crazy for more than 10 years, right? How many survey requests do you get a week or a day? I mean, all that stuff is going into a giant data warehouse, so now we can try to figure out patterns and think that we know something's going to happen based on something that happened in the past or in the data. Does anybody have a comment about that? I'm just curious what you think about that.
Data mining has become such a big business.
I know. Does it ever bother you, though? I don't like to fill out a lot of surveys. I don't have the time, and I feel like all I'm doing is enabling somebody to do something that maybe I'm not going to be happy with. But on the other hand, if it's to make a product better, they're trying to understand to help make something better for us. So, I mean, I go to the doctor, I go to the dentist, and what do I get within a few hours when I come back? Could you please evaluate us? I mean, it just... it repeats over and over again, right? Everybody's trying to measure their quality. That goes into statistical models, of course, too. Okay, last thing in probability is independence. That assumption holds massively in the simple modeling we do here. We're going to be assuming independence a lot, like if I have a different quantization noise source in a network, DSP network, we'll assume that the noise behaves independent from one location in the network to another. Is that absolutely true? No, but it's a simplifying assumption. So it's a property of probability. It's not a property of the set theory stuff. And I don't know if you remember back to when you took probability, you probably were perplexed about independence and being mutually exclusive or uncorrelated, right? I mean, they're easy to get confused. But the thing I always think about is you have to be told independence is true. In other words, this definition right here might come out of the way the events are created. It might appear as if the probability of A intersect B is probability of A times probability of B. But it's not really like in a repeated trial situation. If you roll the die once, you're going to get a face. If you roll the die a second time, you're going to get another face. We would say, as a matter of practice, that each of those rolls are independent, so that the two probabilities are independent. Isn't that a reasonable kind of assumption? And if you go back to the history of prob and stats, way back in time, people were always, the classical definition of probability was everything is equally likely. Now we just need to figure out what are all the possible outcomes and try to enumerate them so we know what the equally likely property is. But then that started to cause problems, and the mathematicians moved in and said, no, we got to make this more solid. And that's when they came up with the axiomatic foundations of probability theory. But back a long time ago, when people would cast lots for things, it was just an equally likely kind of thing. And we still use that idea today. Like, if you are rolling a die, you just say it's equally likely to come up in any one of the 6 faces. If you have a game that has a spinner in it, you spin it around, you say the angle can be any angle equally likely. It's actually uniformly distributed, we would assume, on 0 to 2 pi, but that the angle of the spinner would be theta, let's say. So theta would be uniformly distributed. Okay, and that would be a random variable, by the way, too. So random variable now takes the elementary outcome idea and maps them, rather than just chi, I, and so on, and maps them out to points on the real line, like x of chi I, x of chi 3, x of chi 1. So it's actually a variable, a real number, let's say, or an integer number, but it's a mapping. And the thing about probability is it's not just one line, it could be an n-dimensional space. And of course that engineers use that too, where you run the experiment and you have all these other facets in the random variable context that occur, so you've got multidimensional stuff. And the random variable can be continuous, discrete, or mixed, and that just says that it could be discrete is the die example. If you think about the faces of the die becoming numbers on the real line, they're numbers 1, 2, 3, 4, 5, 6, so that would be a probability of 1/6 assigned to each of those faces. But if you take the spinner problem, like I was describing for a board game, that would be continuous, because you would say you'd spin it and the angle could be anything between 0 and 2 pi. How would you get a mixed case? You generally have to operate somehow or another on the random variable to make it become mixed. You might have a signal that you're measuring, and it might be such that you reach the dynamic range of the measuring device. So the measuring device will clip the signal at the low end and at the high end. So the signal has some distribution, likelihood in some interval, but if it exceeds above and below the threshold, that value will just hold at those threshold values. It'll clip, and that will put a lump of probability or a delta function associated with the probability distribution. So that becomes the mixed case, where you have some of each types, continuous and discrete. The characterization of the random variable is in terms of its CDF fundamentally, which just maps the probability onto the real line and accumulates it from, it's the probability associated with the event that chi sub x of chi is less than or equal to little x. So you draw a threshold onto the line, say x, and then that's minus infinity, so you're going to accumulate all the probability from minus infinity up to x, and then let x move around to different values. Say if x is back at minus infinity, no probability is mapped out onto the real line, so it's 0. When x goes up to plus infinity, then all the probability is mapped out onto the real line, so you get 1. It is right continuous, and it's non-decreasing. It has a property that when I do this in other classes, where like in comm systems 2, we spend more time on this, talking about a CDF in 2 dimensions could be viewed as sort of the ideal hiking environment. I'm going to explain what I mean by that. If you're climbing from Colorado Springs up to the top of Pikes Peak, what do you want your trail to do as you're hiking over land to get to the summit of Pikes Peak? Do you want it to be non-decreasing, or are you fine with it going up and down? I contend I'd like to just always be increasing, because I don't want to have to re-exert and spill energy to climb again. So that would be the nature of the CDF then. If you're moving in the x-coordinate in a positive direction, if you're moving in the y-coordinate in the positive direction, you can be guaranteed, and if it was a CDF type function that you were hiking over, you would always be going up if you increased x and y. The hiking example may not matter a whole lot to you, but It matters a lot to me. I go out walking, I look at the terrain, and I say, do I want to go that way or do I want to go that way? Oh, if I can stay up high and never have to descend because I ultimately have to get to here, that's what I want to do. But maybe there's something interesting, more exercise for sure. So the derivative of the CDF would be the PDF, and that would give us the density function. And that is probably the most favorite scenario for engineers, I think, is we like to think of probability densities. We spread probability over the real line in terms of a density, describing how it's located. It's always non-negative. It integrates or has an area or volume, whatever the type of dimensions are on the random variable of 1. And if we integrate over an interval or a little tiny region, we get, in this case, the probability of x2 minus the probability of x1 in terms of the CDF. But more importantly, we're just integrating that PDF over that interval. In this notation, I didn't point out to you, but this book doesn't use the standard notation that a lot of prop and stats books would use. They would have little f for the PDF, and then they would have big X of x for the CDF. Our book uses little p and uppercase P. I've taught other books that use both, and I like the F and big F much better, but you can survive it. It's just the way some books like to write it out. So what about joint random variables? Then we have a two-dimensional CDF and we have a two-dimensional PDF, and we can integrate over a region, like I said, or integrate from minus infinity on both axes to get the CDF. And then when we have two random variables, we can have conditional PDFs. So we can define a density on y given x and a density on x given y, and then finally you get Bayes' rule down below here for conditioning on one versus another. And these types of things would show up in the more advanced problems, not in this class, but if we were doing hypothesis testing or estimation theory, we would make use of these joint PDFs. And that is a course that I don't know whether it'll ever be taught here again, but I had a class called Statistical Signal Processing that had embedded inside of it, amongst other DSP with random signals topics, it also had detection theory and estimation theory, which are the classical approaches used for decades and decades. And I've been sort of being overtaken by machine learning, saying that we got it, we got this covered. And I say, no, you don't. The classical people were here first. Your ideas are just built upon, what they did. Don't let anybody fool you into thinking what they're doing is something that hasn't been done before exactly, because we've been doing this stuff for forever. When did radar first start to appear? I think it was at the end of World War I or something, and was utilized in World War II a lot, I believe. We had the matched filter theory for signal processing, and then we had the Nyman-Pearson criteria for declaring, for trying to hold the probability of a false alarm constant and then hopefully get a high probability detection. And that concept of the false alarm probability being held constant is fundamental. Think about our national security. If it's going to be a nuclear strike, do we want to just haphazardly have a false alarm and then all of a sudden we're launching missiles at somebody? We want to have a good, solid Nyman-Pearson kind of model where the probability of false alarm is held very, very low, because we just don't want to make a mistake. Likewise, in your car, you have a Nyman-Pearson kind of criteria in there too. You have your accelerometer in a box somewhere in your car electronics that decides about blowing the airbag. I don't know about you, but since I experienced an accident near my home when somebody went through a four-way stop and unexpectedly, I didn't know the car wasn't going to stop and it was going fast, and just bam, just spun the car around, the airbags blew and could have killed my wife. But I think about the airbags did deploy, and it was a scary experience. It's like two shotgun shells going off inside the compartment of your car. There's smoke rising, there's ash and glowing element that fired that. I thought something was going to start on fire because I wasn't expecting that there would be some glowing ash material floating around inside the car. Has anybody else ever had an airbag blow?
Not personally.
Yeah, it's creepy, but it happens really, really fast. I felt like I was on a super amusement ride, and my diesel engined Volkswagen spun around and headed off in another direction. The front end of the car was ripped away, but the diesel engine, if you know about diesel engines, do they need electricity to run? It just kept running. I was trying to bring the car to a stop, and I'm like, the engine, it's still running. Why is that? Well, it's just, it added to the creepiness of the whole thing. If it would have been a gas engine, it could have been a fire worse than diesel fuel, and it probably would have stopped the engine, but it didn't stop the diesel engine. Okay, moments, we're very interested in that for this class, the mean and the variance. So statistical averages would be the first moment of the PDF, and that's m of x. We have mean available for that in MATLAB, Python, and Julia. If we want to go for a higher order moment, then we can use something called the fundamental theorem of expectation, where we replace x by some function of x. It could be x squared, it could be x cubed, it could be anything. And the fundamental theorem of expectation says that we can still use the PDF on x to form that moment. When I used to teach the Prob and Stats class, this theorem in one of the books I taught out of was called the rule of the unconscious statistician. And it was a dry humor thing saying, what would you do to calculate this moment in terms of g of x? You might think I have to go ahead and transform the random variable x into a new random variable, g of x, get its new PDF, which you do learn about in the fundamental class and the advanced class, or can I be lazy and do exactly what this theorem says? So I think that's why it's called the unconscious statistician. It's like, close my eyes, I'm just going to do this. I'm just going to assume that it works. And it does work. You can prove it mathematically. So for example, the variance, the function g of x is right here. And that gives you the variation about the mean. So you're taking x minus its mean and then squaring it. So this is also known as the second central moment. So a moment is a term that comes mostly from mechanics to me. I took statics and dynamics from mechanical engineering. It was required in my era. So we learned about moments a lot, because that's how you can assess a structure, is moments. Forces pulling down, and just look at anything that's being built. And once you've had a statics class and you've had physics 1, you think about, is there enough strength in this vertical to handle this big moment arm out here with a mass on the end of it, or look at a crane, how does that stay in place with the truss of the long crane? Why do I think about that? A little reminiscing here. My office was right up here in this corner where Dr. Lindsay's office is. And when they built, actually they built the library, and when they built mechanical engineering, there were cranes swinging around out there all the time, and they would swing, carry payloads right over the corner of the building where my office was, and it made me nervous thinking about what if this thing falls off the end and comes crashing through the ceiling. It's happened, right? My family went to the Northwest summer of 2019, the year before COVID. We were up in Seattle, and my son is an architect. He went with us on the trip, and he's really interested in architecture. But a few months before we went, there was some building in the downtown area where a crane did collapse, and it fell on people and killed people. So just something to think about. Don't run every time you go underneath a big crane, but I think about it because they can fail. So fundamentally, we liked, besides the mean and the variance, and we have var for variance and STD. Those are standard deviation would be the square root of the variance. Those are available as tools for us. Random variables are said to be uncorrelated if the expected value of the product is the product of the expected values. If the random variables were independent, this would automatically hold because we know we could factor in the fundamental theorem of expectation the joint PDF on x and y into the product of their marginal PDFs. I kind of slipped over that over here, but that would be this right here. But if they're uncorrelated, we have that property just given to us. And that is an assumption used frequently in our modeling. As a matter of fact, it's used essentially all the time when we're modeling with quantization and noise and such. We're going to assume uncorrelated. And in a communications receiver, you generally assume that the noise at the front end due to thermal noise is uncorrelated with the signal. The jammer signal is uncorrelated with your signal unless it's a really smart jammer that's doing something coherently, which would be, more effective, obviously, in a jamming sense. And if signals are orthogonal, then one or the other of them, or both, would have zero mean, in which case, say if just the noise was uncorrelated, so if that one was zero, then expected value of x times y would be 0. This is going to show up in the very first homework problem of set number 5. So the orthogonality idea is brought up here because in terms of abstract vector spaces, it's nice to be able to think of random variables in the context of abstract vector spaces and the inner product. Remember that from linear algebra? You have a vector x times a vector y, and if they're orthogonal to each other and you form the dot product, what do you get? You get 0, right? So in an abstract inner product space idea from linear algebra, the expected value of x times y is viewed abstractly as an inner product. If I was to go down that path, it'd all be about the advanced statistical signal processing class, but it just shows you how engineers have leveraged that, especially EEs with statistical signal processing, that idea of orthogonality. There's actually a property in estimation theory that says, the orthogonality principle says that if you have a noisy observation of something of interest, like you're trying to estimate velocity, an aircraft is trying to estimate velocity as it's approaching a landing, it's using its own internal nav system, but it might also get information fed to it from the tower saying, we see you, your approach radial has got a velocity of thus and such. So they might decide to fuse those two pieces of estimates together to form your true velocity estimate. But let's see, what was I going? I lost my train of thought on that one. Uncorrelated. We'd assume that the measurement from the tower is uncorrelated from the measurement of the inertial system. So they could fuse together with an assumption of uncorrelatedness, which would be helpful. Because otherwise, if they're correlated, then the measurement could actually go really bad. If they were anti-correlated, in other words, with a -1, then they would cancel each other out, and it'd be like, we don't have an estimate. You know, we have no confidence right now. Obviously, though, when you're taking measurements, you want correlation between the observation and what you're trying to estimate. I know what I was going to say. I was going to talk about the orthogonality principle. The orthogonality principle says that you form your estimate to be in such a way that the data and the error are orthogonal when you form the optimal estimate. If the quantity you want to estimate is something up here in space, and your observation plane is down here, and you have noise on it, you drop a perpendicular bisector down to this observation plane, and that will be the minimum error, and then the line that goes out to the point that drops down will be your optimal estimate. Okay, important PDFs, uniform PDF we use a lot to model quantization effects, and if we're modeling in systems with noise at the front end due to random electron motion, which is always present, then we take the central limit theorem ideas of saying that a bunch of independent or at least uncorrelated random variables will appear Gaussian after we sum them up. And I'm going to give a little demo of that in Jupyter here in a second. Just as a refresher, though, since this is going to show up in the homework, what is the mean of a uniform random variable, just from memory? What's the central value that it takes on? Just looking at the PDF, this is why EEs like PDFs. You look at that and you say it's equally likely. So should be that, right? Just the average of the two endpoints. This one was probably a homework problem. How do I remember it? I remember it like this. I say that if the distribution has got some width to it, delta, the variance is going to be delta squared over 12. To prove that, you have to go through the definition of variance and use the PDF here that's uniform on A to B. Does this bring back a memory from the class? I want you to just, you don't have to prove it. In the homework problem, you don't have to prove it. You can just remember that it's delta squared over 12. And another thing about prob and stats, or random variables here, is that units can save your bottom. If you're doing a variance calculation, whatever the dimensions are on x are going to be squared and then divided by 12. So the units on the variance are the square of the units on x. Like if it was in meters, it would be meters squared. If you form the standard deviation, that's got the units of the quantity itself. So if you square root this, then you will have delta over the square root of 12, and that will have the units, say, meters, not meters squared. So those sorts of things can save you, because you will say, why is this number so tiny? Oh, I didn't take the square root. It's got, the different units. Suppose standard deviation was supposed to be 0.1 meter, and it was 0.01, and you're like, why is it so small? Well, the units, are meters squared. So has anybody ever been there before where you get the units messed up and then you just think back, yeah, that's right. I can't mix meters squared with meters. That has to be consistent. Gaussian PDF is the bell. Wider bell means larger variance, more uncertainty. Narrower one focuses it on its mean, which the largest point is when the Gaussian PDF's argument is 0, or mx in this case. This is the shifted version of the Gaussian PDF. The tails of the Gaussian PDF are given in terms of the Q function, and that can be written in terms of this integral here, which this could actually be written in terms of a special function called the ERFC, complementary error function. I'm not going to really go into that. I'm not going to be having you do anything with it in this class, but I'm just pointing out that that is a popular topic. We have the ERFC available in MATLAB, it's available in Julia, and it's available in Python. In Python, you actually have to get to it through the SciPy package called special, which is special functions, which would be a function, namely that integral right there, evaluated to get the ERFC. That's the conversion to get Q from ERFC. Okay, now we're going to look at random processes. So I reviewed this a little bit last week. This is like the full deal right now. So now we're going to build up to the idea of the random process, and I'm just going to jump right to what I was looking at last week. It's taking the elementary outcomes from the sample space and now mapping them out to a collection of functions on the time axis, space axis, whatever you want to use. Here it's a discrete time random process idea, but it could be continuous time, like if you're looking at the receiver in analog electronics front end, it would just be a waveform that has noise on it, and you would model it as one of an infinite number of possible waveforms that you could see because of, if it's signal plus noise, the signal has variations in it, and the noise would be, say, due to random electron motion, and it's very unpredictable. So we get a whole family of sample functions, and you characterize this ensemble in terms of means, autocorrelations, and variances, and autocovariances, and so on. So you sample vertically, take a vertical slice, and that gives us the random variable. So this is what we'll mostly be looking at. But then we'll also look at, I'm getting on my watch the political text messages for the candidates right now. I've been wondering what that's all about. My neighbor up the street is a councilman that's running for a position, and he's been sending out a lot of his messages. I never see him because he's always wearing his coat and tie down at the city council meeting, but he's acting as most politicians would. City council is a stepping stone to his next position. He's an Army guy. He was in Special Forces, I think. And now is developing his political career. So we'll also do slices at more than one location. So we'll go for the autocorrelation. We're going to see that in just a second. But individual sample functions are the horizontal, and that would be measuring equipment would be able to take just a collected record and do a time average on it. If we're doing a statistical type measurement, let's see if this will keep working for me. We're doing it vertically, and we'll be just characterizing it at a particular time instant. And that is the kind of the modeling domain of random signals. In the measuring domain, you collect just one sample function because that's all that really ever occurs. The ensemble is just to give you the flexibility of saying what are all the possibilities that are out there. One of the graduate students right now is modeling an adaptive filter called a Volterra filter, and he's having some issues with a adaptive filter algorithm losing convergence and actually going chaotic. And I'm kind of upset with the way things are going for him right now, but at any rate, he wrote to me last night in Slack and said, I still have these occurrences where it produces lots of errors through this adaptive equalizer, which is trying to remove nonlinear distortions put on by traveling wave tube amplifiers in transponder satellites. And I'm saying they're just occurring sort of at random. It's like one interval where he's simulating a long record and chunking it up into sub-records to make it more manageable for processing. And it can't happen. I mean, I worked on a system many years ago at RT Logic that was doing an adaptive filter, and we had to put in an algorithm to control the convergence parameter so that if on the rare occasions it tries to go unstable and blow up, you stop it from doing that. We can't build a system where we let it just sporadically glitch like that. That's unacceptable. I mean, that would be loss of data, but if it was a scenario like adaptive control and it was a fighter jet, it would be totally unacceptable to have it lose stability and crash a plane. Or Elon Musk and Tesla's having accidents when they're autonomously driving. It's kind of a similar idea. So we characterize, though, and we're using just one time average in a measurement scenario and in a practical setting, but the statistical modeling is so we can explore all the possibilities for a system. Boldface X is what I like to use in the notes, but the book typically will just use little x, and you have to get from the context whether it's the random process, whether it's a random variable. Because you see, if it's x at time n, you'd say, oh, it's just at time n, and I'm characterizing one sample function. So you just have to get it from the context, which of these four it is. So how do we characterize random processes? Well, we treat them in the statistical sense, just like a random variable, but it's parameterized now in terms of n, which in the continuous time case would be time t. So the way we manage this is just consider n as a parameter. So if we fix n, we can calculate the mean and we can calculate the variance. If n changes, in general the mean will change and the variance will change. If a process is stationary, though, then it will be the same value at different values of n. On my website, I've got the waveform running in the background. That was created in MATLAB many years ago. It was a filter charging up with noise, and behind the magenta coloring there, it starts at 0 behind that, and then as it charges up the filter, it gradually builds up. So if I was to slice down here vertically and take the mean here, and then if I was slice over here and take the mean should be 0 no matter where I take it, but the variance as it's charging up, you can see there's less spread of the 4 sample functions, and there's a bigger spread over here. See that? How that's happening? So what we do in this class, though, is we're assuming we're in steady state, where things are charged up already. But there are transients as noise is building up in a system, so that's just the nature of it. We're going to call a process to be stationary if all the moments, the mean and the variance, are independent of time. So that's just constants, and that makes life easier for us. What we just have to do in simulations is not take measurements early in a simulation. We want to make sure we're at steady state. Autocorrelation sequence is a step in a more complex understanding, and that is where we're going to take the 2 random variables that we get in this picture here, the red and the blue. It's like I have a random variable interpretation if I slice down at times n, but if I slice down on a different time n, I get a different random variable in general. I mean, all these vertical slices in the ensemble are like different random variables associated with one random process. Does that grab you? It should, if you're just casually thinking about it, it's like, okay, fine, but if you start thinking harder about it, it's like, wow, I'm now going to have an infinite number of random variables if I sample at all these times, or I'm going to have hundreds of them. Potentially, yes, but we manage it, so it's kind of daunting to think that way, but the autocorrelation sequence now slices at two different locations, n and m, and to manage the complex case, there's a conjugate in there. And the autocorrelation then is going to be a function of both n and m, which auto means self, and that notation means x and x. So it means we're correlating x with itself at the values of n and m. Autocovariance, it just extends that by subtracting the means off before you take the autocorrelation. So just going to subtract the mean off. And then, in fact, the autocovariance when n equals m just reduces down to the variance that we've already talked about. So it would be the variance of the random process at some time slice n. If we have wide sense stationarity, which is what we have in the book, then we have a simplification. We're going to have the mean a constant, the variance a constant, and the autocorrelation and the autocovariance are just going to be a function of time difference m. And so m is, in this notation here, we'd say the autocorrelation is going to be evaluated at m plus m, the first time argument minus the second one. So it's a function of m. That's a way of working problems. And there is one homework problem where you bump into a little bit of that on set number 4. So take the first argument minus the second one. You know that you can reduce it down to being a function of just the time at the first sampling instant minus the time at the second, so you will get something like this. Just a function of the time lag. So depending upon where the samples are taken, these are the samples. If they're at the same time, you get the variance. If they're lagged slightly, you get the autocorrelation, well, the autocovariance if you subtracted the means out too. If the process happens to be zero mean, then autocorrelation and autocovariance are equal because this term, the mean, will go away. If you have more than one process, or if you have an input and an output of a system, then you can look at the autocorrelation between the input and the output, and that would be, say, x and y. So that would be x at n plus m, and then y, and that would be a cross correlation. And that can be useful for determining whether or not there's some coupling statistically between two signals. And why would we care about that? Well, if you're estimating from an observation, that has got to have something related to what you're trying to estimate, and the cross correlation is going to hold the information that you're looking for. You can also define cross covariance by just subtracting means out again. If a wide sense stationary process is uncorrelated, which means that the expected value of x times y is jointly uncorrelated, that means that product becomes just expected value of the product becomes the product of the expected values, which is convenient. And that is a popular assumption for us. And if either process is zero mean, then that becomes zero. That would be a popular situation in a noise configuration. The next definitions are something that is really important. It says if we have a Whiteson stationary process, and that will be the assumption always here, then the Fourier transform of the autocorrelation function gives you the power spectral density. And simple SA, which is what I'm having you use in problem number 2 of the project, is forming an estimate of the power spectral density, just to let you know. There's also another function that MATLAB has, PSD, which they kind of deprecated. And also in Python. Python has a PSD function similar to what MATLAB had. MATLAB kind of deprecated it. They want you to use a specific spectral estimating function, which is kind of why I decided to create my own simple SA, because I wanted to have the spectrum analyzer be more controllable rather than you just plugging into it and saying, oh, that looks nice, I'll take it, but not understanding what it's doing behind the scenes. Pretty much the most common technique is to use what's called an average periodogram. That's in one of the advanced chapters way past the end of the notes here. So I'm just trying to keep you a little bit in control of not going crazy with it. But you know, if you're playing around with a problem at work or something and you want to just run PSD on a signal, it will form a spectral estimate, and it will be a scaled version of the power spectral density, which means it will have units of the signal quantity squared. It might just, in a dB axis, it will be moved up and down based on some scale factors. But then, of course, you can inverse transform the power spectral density to get back to the autocorrelation sequence. The expected value of the magnitude squared of x, which is when you're taking x times n and x conjugate of n, same time sample, will be the autocorrelation function evaluated at 0, and that is just equal to the area underneath the power spectral density. That's a real important result, because that would be another way of getting the power in a signal if it's 0 mean. Also, from a measurement standpoint, referred to as the AC power. Now, on the measurement side, when you're working with real signals, we have to be content with working with the horizontal one sample function, the one that we get to capture when we're taking measurements. We don't have the vertical slices, which is the abstraction, you know, of probability and random processes and stuff. We don't have that abstraction of getting the random variables and looking at the correlation and stuff like that. Instead, we have to substitute that with the one sample function that we capture and form a time average on it. So this is the time average mean then, and then the time averaged autocorrelation function, with the notation meaning the angle brackets there just means you're going to replace that with that guy, and you put whatever you put in the angle brackets is what goes in that sum. In this case it was x. In this case down here it was x times x conjugate with a lag in there of m samples. In Com Systems 1, and a few of you have had that class, we have the time average operator in there. And this is that exact same thing. We're just doing a time average. So how does this come together? I mentioned statistical, slicing down vertically, and now working with a sample function, having it horizontal. That's this bullet right here. Like to have ensemble averages, which is what we get when we do the vertical sample space stuff across the ensemble. equate to time averages. So the way that happens is, if it's the mean that we're looking for, we have to have the process be mean ergodic. And so the statistical mean and time average mean are equivalent. And if we want to have autocorrelations and cross correlations hold, then we have to have correlation ergodic. This is all pretty high level mathematical stuff in terms of theorems and what are the detailed requirements to make these things hold, but I'm just wanting to say we're going to assume that's true. And what a practicing engineer has to do is, if you start going off the road too far in a setting, things might not work properly because you've voided these assumptions. But the idea of ensemble averages, what you can model on the computer, the vertical random variable model stuff, and what you can do with measured data when they do a collect for you and deliver you some sampled data, you can assume initially that you've got these ergodic properties. So mean will hold across the two different interpretations, and autocorrelation will hold, and hence then power spectral density will also be computable on both sides and be equivalent. The stipulation, though, with the time average always is that you have to assume that L goes to infinity to have the time average really match the statistical average. And that up here says that you've got an infinite amount of data. So both of these equations require large amounts of data. So you do not get quality estimates unless you have a lot of data. And in a practical application, like in a radar system for target identification and so on, you can't just sit there and collect forever and forever before you make your decision, is a target present or not. You have to go process the data and say, I think so, but I only know within some statistical uncertainty, because to take longer would be, I don't know, is that reckless endangerment? Not knowing that you're about to, well, I guess think about your car collision system. I think about my car and how it screws up every now and then. It's a 2017 Toyota, and it still freaks me out because it flashes a bright orange thing in my console when I'm coming around the corner. Same spot in my neighborhood. If there's a parked car over there, it will occasionally go, stop, stop. It just go, it doesn't send off an audio alarm. It just flashes really brightly in my face. It's like you're going to have a collision, and I'm going to go right by and it's going to stop. Or it's that type of thing. If it had to wait longer to get a better measurement, it probably would say, no, there's nothing there, but it just couldn't get an accurate enough measurement, so it was trying to warn me. It doesn't try to put on the brake, though. But I think newer cars probably give you the option to do more. Mine does have that steering control, though it will try to wake me up if it thinks I'm across the line or something. And many of you probably drive cars like that, where it has that stuff you can turn on and off. At any rate, lots of samples makes things better. We actually get biases in the estimate, just commenting on that, if you don't have L large enough, and then you can remove the bias with extra processing. So I want to go one step further, and now we want to talk about random processes going through a system. So this is going to be X going through a filter or some sort of discrete time system. What happens when a random process goes through a system? Well, we do have to worry about using linearity in the expectation operator, but we know it's a linear operator, so we can do the expected value after we convolve in this case. So the mean on Y, you see it will become the mean on X sent through the filter, and if we assume the signal is wide sense stationary, then we know that it doesn't matter what n minus k is, I'm just going to get a constant mx. So then I'm just taking the mean of the input times the sum of h of k, but h of k summed over all values of indices will give me h of e to the j0. And what is that? Systems-wise, when you set frequency equal to 0 in the frequency response, what is that? DC, right? So I want to drive a really obvious point home here. The output of a system, the mean at the output is going to be the mean at the input times the DC gain of the system. And that makes perfectly good sense, doesn't it? I know there's a lot of definitions and things I've been going through, but that makes really good sense. And that also just reminds you that you can get the DC gain of a system by summing up its impulse response. If you want to get the autocorrelation at the output, it's going to take a little bit more work, and this is just the definition of it. It says that it's going to work out to be the autocorrelation at the input convolved with the time reversed impulse response and the impulse response itself. So you're doing it twice. And the proof of that kind of lies, I guess I didn't put all the gory details in here. It lies in some more writing that you can do where you expand it out. You're just substituting in, though, what is the input autocorrelation function. You're going to now convolve it, but you have to convolve both inputs in the autocorrelation function. You have x at n plus m, you have x at n. So both of those x's have to go through a convolution with h to get y at n plus m and y at n. So that's why in the end here you see a double convolution with the impulse response. One is flipped around, though, h of minus m and h of n. And that leads to an interpretation for the autocorrelation function at the output, saying that it's the autocorrelation function at the input convolved with something called the autocorrelation sequence corresponding to the impulse response. And that's just this part, which is that's a deterministic quantity. That's just something you can calculate. I have an example here in the notes, and I checked that out in Python, of inverse z transform of h of z times h of 1 over z. This is the one instance where one of those theorems that was discussed in chapter 3 gets utilized. What is the region of convergence of h of 1 over z? And we'll see that in the example. If you take the autocorrelation at the output and Fourier transform it, and then Fourier transform what's on the right-hand side, we'll get this very important result. And that's probably one of the most important things. It's something that in the lab you started talking about it last week when I was talking about how to characterize a filter in terms of the power spectral density at the output when you're driving the input with white noise. It makes use of this result right here. It says that the output power spectral density is going to be the input power spectral density times the magnitude squared of the system's frequency response. So if we want to discover what the magnitude squared of the frequency response is, we can just pass white noise into the system that has a flat spectrum, and then the output power spectrum will be equivalent to a scaled version of the magnitude squared of the frequency response. What is white noise? It's just noise that has zero mean and is uncorrelated. So zero mean and uncorrelated means that the process has got its autocorrelation function of just being a delta that turns on at m is equal to 0, and the height of that is the variance of the noise, sigma w squared. And so if you Fourier transform that, you get this relationship here, that the white noise autocorrelation function transforms to a constant spectrum, which of course has periodic extensions. Normally you just think of it as being on minus to plus pi, but it's flat. Why is it called white? It's interesting these days, but it has to do with white light. That's where it came from. It has nothing to do with race, which I always find it intriguing, because in our society today we're so sensitized to just about anything and everything out there. But it's flat, meaning white light. And if you shape a noise spectrum to make it be not flat, it becomes colored noise, because it's like if you shape white light, you can pull out a color, right? Red, blue, or green, or something like that. Okay, so I have explorations. Originally this was done in MATLAB. I have it in Python. I think I'd just like to do it in Python so I can dial through all of this stuff. And there's one part of the example, though, that's utilized in the homework problem, so I want to come back over and look at this. I guess because it's right now at 9:30, we could take the break right now, which would be more normalish, and then come back and do these examples. Does that sound good? If you're needing the break because you're needing it for whatever reason, let's just do it right now, and then I'll come back. Okay, we're over here in Jupiter, and I've got three things I want to look at. I'm going to take a little tangent off into the project for a little bit here, and then I'm going to come back in to chapter 4. So I've got 3 tabs open. We're going to start with project 1 sample file, which has got problems 1, 2, 3, and 4 on it. Then we'll move over to just problem 5, which is real-time DSP using Pi Audio Helper, a really fun area that I want you to have fun with. I mean, but you gotta, I'm going to have to give you some basics. I'm going to start with that today. But here's where we were last time. This is how I patch things up. This is how I bring that file in, which is sitting in my folder down below here. You can see it was put in on October 20, whatever the date is on there. Simple SA new. So what I did is I ripped a function out of Scikit DSP's one of the modules, and I just put it into a file all by itself. I read about what Python SciPy has been doing, and I made some fixes. So I imported here just with a shorter name, SA new, but it has within inside of it the desired function. So if I go over here to problem number 2, I now can use simple SA just like I did before, except now it's in this module that has a first name of SA underscore new, whereas before it was just SS. SS is still there. It's liable to not work, and it has something to do with the way they've changed the naming conventions of things that are in scipy.signal. They now have a separate module called scipy.signal.windows, and within that is where the windows reside, but that isn't the way it used to be. So I'm doing things differently, and principally they did this as well. They changed the names of the windows. I used to be using Hanning, which is actually very crude terminology. The guy's name is Han, H-A-N-N, and when he invented this window, it's got picked up by the community as, oh, it's Hanning's window. You understand how that name got convoluted? His name was not Hanning, his name is Han, and they started saying, it'd be like saying Wickert's window or anybody. That was not a really professional thing to do, so they had two windows in there. They had Han and Hanning, and Hanning doesn't exist anymore because it's like you were abusing this guy's name, so they just have Han in there instead. So I had to fix that, but now the good news is if you go do Shift Tab on this, you can see that you can put in any type of window you want to, and I lead you down here to a link. If I clicked on it right, I probably didn't click on it right. It doesn't really matter. You can see all the different names of the windows that are available in the catalog in SciPy.signal. So I'm using that in here right now, and it's doing its job. So it's getting the spectral estimate. And what I was going to do really quickly here, the purpose in this problem is to go ahead and look at the time domain and then the frequency domain using Simple Spectrum Analyzer at this point and at this point, and then finally after an interpolation low-pass filter. Going through the motions to do this is pretty straightforward, and I'm going to do a little bit more of it right here. The harder part is actually getting the theory to match, to verify that the theory is what you're measuring. And that requires just doing math. And you can do it on the computer here if you want to, and that's the way I chose to do it. So as a matter of fact, I think I create a vector in here that just has the two frequencies in it so that I can manipulate it around. And I think I'm going to show you that in this comments page. Remember I said I started working on a comments page for these problems. It'll just be some comments for each of the problems. It'll tell you about some techniques. And I'm going to try to emphasize the pitfall areas, the areas where I've seen people fail frequently. That's what the comments are going to be on. So you're going to have to be engaged in the problem enough to know what the comment is. It'll hopefully help you out to see, oh, there's a comment here. It must mean that I'm giving you some comments because I know that you can go off the deep end if you're not careful here. But just to give you an idea, I made a copy of that cell and I have it right in here. So I'm just going to go. So I just typed a few letters and then hit tab. So I'm going to downsample X by 4. And then down here I'm going to take Z1, hit tab again, and I'm going to put Z1 in there and put 4 in, but I didn't want to do that. I wanted upsample, so back up. Okay. I hit tab just for good measure and see that it just retyped it. So now I'm going to generate, I'm going to downsample, which will introduce some aliasing for one of these two signals. And then I'm going to right away upsample it, which is going to produce 4 images. So rather than looking at the interstage point, I'm just going to go look right at this point. The amplitudes are a little bit different, so I might want to change my scaling here and let this be, well, let's see. Yeah, minus 30 is good, but I want to stop at minus 15. Okay. So what are we looking at here? We're looking at the result of taking this spectrum, and when we downsample it by 4, we're going to create some aliasing. It's still going to contain just 2 spectral lines, but one of the 2 frequencies in here, namely this one, is going to fold because we're downsampling. The downsampled rate will no longer have that higher frequency at below the folding frequency. So pi over 3 here is going to be greater than pi over 4. Does that make sense? When we remember, the cutoff frequency or folding frequency of the anti-aliasing filter has to be at pi over m. In this case, that would be pi over 4. And we have a sinusoid that's at pi over 3, and which is greater than pi over 4. So that one is going to be sitting up here at pi over 3. It's going to fold about pi over 4, and it's going to end up as a principal alias down below. And then it'll be 2 spectral lines, though, that you'll see. But then when you upsample by 4, you get images of the spectral signal that's in here, which is 2 spectral lines, but it's not the same as you started with. And then you get 4 replications of that. So that's what we're seeing here when we upsample by 4. We get a pair here, and then we get another one here, another one here, and another one here. And you can see, if you can kind of get your brain wrapped around the idea, the way this is happening, it's kind of like paper is being folded into an accordion fashion. The first one is high, low, and then the next one is like a mirror image of it shifted up. So it's like it accordioned around, so it's low, high. And then the next one flips back again, high, low, and then the final one up there is low, high. It's the images that are getting pasted down, 4 of them. What you have to do is you have to use the find peaks function, which I didn't run that in here at this time, but it's in another example, doing find peaks to see where those peaks are. But then you have to mathematically figure out where these peaks are going to go to. So you have to take the 2 frequencies that you have down there at the fundamental interval and identify those correctly theoretically, and then you're going to shift them up by factors of pi over 4, I think it is, or it's pi over 8, I think, actually. And then you're going to be flipping it or not flipping it. And I wrote up a couple of lines of Python code just to get those 4 frequencies, and then you'll have it theoretically. You'll say theoretically, I know where these 8 frequencies are at, and then I use find peaks, and I get where they're at. Now, if you remember over in here, I did have an example in here. I just didn't go back through and do it. I did use find peaks. Remember, you'll get some kind of display like this, and now you'll identify 18, I mean not 18, but you'll identify 8. And what you're going to do is you're going to set your threshold when you do find peaks, set it at about -20, and that should find just those 4. There's going to be a bunch more peaks that are way down here in the noise. Set your threshold and find peaks so that it's high enough that you don't see all that kind of rubbishy stuff. That will be that number. You'll change that number. This is an example that's in the Chapter 4 notebook. So I'll propose a little bit about how you can, or comment a little bit about how you can identify those theoretically. It comes out really, really nicely, though. It comes out almost perfect. I mean, no, it doesn't show accuracy out to 4 decimal places, but it will at least be 2 decimal places of numbers, if not more, in the find peaks when you run that. Okay, so the next thing I want to go to, and I'm going to try to write comments for the other problems too. Next thing I want to go to is Pi Audio Helper, because those of you that aren't in the lab or haven't taken real-time DSP, you need to understand a few things about what's going on here with the Pi Audio Helper. We're basically using Python and the audio subsystem of your laptop to create an environment for writing a real-time DSP signal flow. And you write an interrupt service routine effectively in Python code, and it's called a callback function. So the first step in all of this, though, is to run this part. I think I was using PyLab inline, and I added these statements on my own. Just the current one pushed in there is somewhat older header here, but you'll get a deprecation warning. But other than that, because Pi Audio Helper is garbaged up, I'm not happy with it, but it still needs to be fixed. I've got this module in here. And if we go back to here, we have this guy, Pi Audio Helper old, the old version of the code. And so I'm importing that with the same name that I was using for same shorthand name or alias PAH, Pi Audio Helper. And that should work just fine. I'm running on my system right now the virtual environment that's installed in Julia, just like we went through early in the semester. So I'm running that version, which is Python 3.10. Sound device helper turns out does not work. Last fall I thought it could work, and when I was doing testing early this semester it doesn't work, so that line could be scratched. The rest of these are imports that are just needed to do the rest of the problems for this problem number 5, which has parts A, B, and C. If you didn't get this installed in your virtual environment inside of Julia with Conda, you have to install IPy widgets also so that you can get the GUI controlled. So those are loaded in. This is a pictorial of what the system looks like in terms of being able to take inputs and give outputs. This blue box is where you write your code that's going to process in real-time frames of data. And in order to make things work properly, you have to use global variables in Python so that you can get variables from the workspace into the callback function, and that's where you set states for the DSP, and then also you get IPython widgets so that you can have slider controls to change things while they're running. The very first step, though, is to search for available devices. So on my system this morning when I came down here and put my dongle on here, which has my audio device that my microphone's hooked up to, things changed because now there was an additional device. So I had to restart my notebook, which I didn't do. I did that when I first came in here this morning so that I could find the new devices. You have to do the same thing with this Pi Audio Helper. If you had a notebook running and you pulled a dongle off or some other device off, the list of devices will change and the indices will change along with that. So you just gotta, the best thing to do is to restart it because you'll just get an error message if it doesn't know about the devices. So for me, I studied this device list carefully, and I wanted to use my audio device, which is the dongle that my microphone's on, and then I was going to play back from the output of that device into the speakers that are overhead, and it wasn't working properly for me, so I said, nope, I'm going to do a conservative thing. I'm going to stay with the onboard system on my laptop here, and that's Realtek Audio. So I noticed Realtek Audio has inputs, according to Microsoft's listing, 4 inputs. I don't believe that's really what I have available. I have 2 inputs. I have 2 channels of line in, or microphone in. And then I look down the list and I look for something else that's down here that I can use. I see a USB audio device with 2 outputs. That would come out of that device. I don't want to use that, though. I'm going to go down to Realtek. You want to go with the lowest numbers. There's a lot of things listed in here, and these high numbers typically don't work for me. They're funky. I don't know what's going on with Pi Audio, which is the underpinning of Pi Audio Helper. Actually, Port Audio is the underpinning of the whole thing. But I try to pick the lowest numbers possible for the devices I want to talk to. So I'm going to go with Realtek. Speakers, headphones. It says it has 6 for multi-channel sound. I'm just going to pull out 2. At any rate, I'm going to use index 2 for my input device, and I'm going to use index 5 for my output. I'm sticking with the onboard audio, Realtek. Okay? On a MacBook, it's not going to work anymore unless you can plug an audio dongle in that has 2 channels, because Mac has now changed things with the newest Macs. The microphone is listed as only 1 input, and it used to list it as 2 inputs. That doesn't work for us anymore. So we have to have, for stereo work, we have to have at least 2 inputs, and it depends on your laptop. Stereo is only being used in one of the problems, but it will have an impact on you. So I picked 2 and 5. Down below here, I use the widgets, and this is where I'm just creating some widgets that have a float slider, so I can change parameters. You can just pick up the notation here, min, max, initial value, step size, and if I want to see the widget's displayed right here, I can just uncomment that and I'll see, okay, I've got a slider set up and I've got some parameters changing. I don't really want to have the widgets displayed there because that's not where they're going to be useful to me, but you can just check them to see if your widget code is working. Next thing is the callback. The callback is like an interrupt service routine for microcontrollers work. The callback is a function that's defined in here, but it has to follow a pattern which is set by Pi Audio. So that in this handshakes with the audio on your Mac, Windows, or Linux machine. It's a universal interface that Port Audio has created. It has an in data, a frame count, time info, and status. I don't use all of those, but they come at you. The callback has to be set up this way. I talk about that in the project reader. And then I've created some globals in here. So I have DSP.io, which is an object that I want to take data out from after the callback runs. So the DSP.io is created initially down here. I create an instance of a DSP.io stream, and this is the corresponding object. It's set up to say, use the callback function of that name defined in the cell above. Use these as my ports. Input is 2, output is 5. Use this sampling rate, and I can set the capture time. If I set the capture time equal to 0, it will run forever. So I'm going to do 0 for right now. And then when I finally get ready to run my stream, I call interactive stream. It has 2 parameters. The first one is how much time I'll capture for. If I set it to 0, it captures, tries to run for forever as well. And the 2 here just means stereo. You can always do Shift Tab and you can see what the options are for you. And then here is where I place the widgets. So the widgets will come up right underneath these start and stop stream buttons, which are put up by the DSP.io interactive stream method. So I want the widgets to be right underneath that so that I can use them while my code is running. Does that make sense? It's pretty cool the way it works. So in this case, I'm not doing anything too exotic. I have some instrumenting code in here, kind of like putting a logic analyzer on this callback to see what's going on while it's running. This thing, like I said, gets called by Pi Audio Helper because I register the callback function's name in here, but that is pushed down inside of your system. You have no control over it. It's guts of your audio system. And then the audio system knows to pull the string on this function callback when it's got a frame of audio samples that need to be handled. You don't control that though. It manages that internally. It's part of, in Windows, the audio subsystem, and on Mac it's Core Audio, I think is the name of the software interface. So there's some things on the inside of this which are mysterious. But fundamentally, in this case, I'm not going to use the input samples, but I do want to stream 2 output samples. So I have a frame of data here, which is going to access another object that I created in the initialization down here. I loaded up a WAV file for testing, and this is just a stereo record. It's 2 columns of data over many samples at a sampling rate of 44.1. And I load that into this loop audio class, and it gives me an instance of loop audio, and I call it xloop stereo. And every time I go into my callback, I just simply say get a frame count's worth of samples from this object, and frame count is the number of samples that have come in on my audio frame, and that was established by default down here when I set this guy up. The default is 1024. So 1024 samples is the size of the frame, and I set that as the default. No need to worry about that. But so what this nice little class does is it pulls that many samples out of this xloop stereo object. So imagine a long buffer here of samples in it. It'll grab 1024 out of it. It loads them in to get played out through this callback, but then the next time I call that get samples, it grabs the next bunch, so it keeps them contiguous. When it gets to the very end, it'll grab whatever is left over, and then it comes back to the beginning. It just loops it continuously, and it just keeps doing that. You don't have to worry about it. I've managed it already in a loop fashion like that. So that's why I call it loop stereo. Then it's stereo, so I get access to all the rows in that buffer, column 0 and column 1, and then I scale them up by 20,000. And this is because the samples from the WAV file are scaled between plus and minus 1, but in this audio subsystem interface, we have to work with signed 16-bit integers. So we need to scale it up into a range of an int 16, and that is done right here. The full range is plus and minus 32,000, right? 2 to the 16th minus, or 2 to the 15th minus 1. So that's just to get it up into a good active range. And then down here I take and do the same thing with these arrays, and I apply a gain value from the slider up above and just get access to it object-oriented wise. I have this left gain and right gain, and it has methods associated with it. If I go Shift-Tab on it, it'll tell me it's a float slider, but if I was to just sit right there, I guess it doesn't do that. All I know is you want to use value to get the value of the slider. And then I pack everything up and send it out. I do a capture, I add it to a buffer, which I don't necessarily use. I only use infrequently. Take it back to an int16, casting it from floats back to int16, and then mark time in a callback to create a time buffer. And then what happens down here at the very end is totally Pi Audio stuff. It converts it to bytes, and then it also sends a message to Pi Audio under the hood saying continue. In other words, keep this interrupt running, so it's going to keep continuously running the callback. These are all things outside your control. Don't tamper with that code because it's the secret sauce that makes it work. So I will compile that callback, and now I will compile this. And if you get a failure, you don't get buttons or something, or if it fails, the next time you do start streaming, you may have to recompile this again. And this interface right now has got a buzzing problem, and the right channel is not working through the audio interface. It's something going on in this wonderful box here, which they didn't really, they messed it up last week. They didn't put the cables in right, so I had to use had to use my own cable. You can hear the buzz in there though. It works though, right? So let's just go to the capture buffer briefly. If you decide to capture for 10 seconds, which I did, I filled the buffer up. But I didn't do it that time, so I have to go in and change this. Let's make this 5. I recommend you not using this unless you need to capture the buffer. Then I could set that to 5. It stopped because I told it right in here, stop after 5. It's not good to leave a number in here other than 0 because it's going to be putting things into that buffer, and it's eventually going to, if you put a lot of seconds in there, it's going to, your RAM's going to run out. It's just going to keep pushing it into a buffer, and it's going to choke on it eventually. But I did that just for this one example, so I can go down here and read the buffer. So it looks like I only got 2.5 seconds, but there's the buffer of audio that got put in there, and then I did a spectrogram on it of the audio. And then if I go down here, This is totally off the map. You don't have to touch this at all, but if you're interested in how the audio subsystem is working, I'm keeping statistics in the background, and this just shows you how the PC audio system is keeping up with calling the callback and dealing with latency and things like that. In order to keep going, it's got to keep calling so that the audio stream can come out and sound like it's in real time. But statistically, it should be taking this much time between callbacks, because that's what it mathematically has to do at 1024 samples. You can see that sometimes it takes longer and sometimes it gets the job done faster. I find that to be kind of horrid, though. If you were building a hearing assistive device, which is, I got interested in this with that, that's not very good. But what is our PC doing? Managing mouse clicks, managing my video recording right now. I mean, it's doing a lot of stuff. So I did this for myself pretty much when I wrote this package years ago. So now I'm going to briefly look at the chirp class. So this is a chirp class for making radar linear chirps. You've got to compile that. It's in the notebook here. And if you run these cells, you will see that I'm creating a chirp. Like every 0.4 seconds, it's going to chirp again. So the chirp period is 0.4. The stop frequency is 3,000, and I start at 2,000 and went to 5,000 initially. These are some of the other attributes that are inside of here. This is part of this first problem now. I'll let you read about that, but I wanted to give you some helps down here where you have to run this in real time. So when you run it in real time, I want you to put up all the sliders that you see right here. You're going to have a bunch of them to control things, and then you're going to amuse yourself, hopefully, by these strange sounds that the chirping is going to make. I just did a little bit. I added a set period in here, and I did some simplifying things. So here I just added one more extra block to the widgets. And then how do I modify my code in order to make it play back my chirp? Well, if you look down below here, I supplied this cell in the sample notebook. I modified the upper cell to make progress towards what you have to do rather than giving you a blank slate. But I create two instances of the linear FM frequency modulator with these different initial conditions. And then I'm going to go ahead and go to my callback, which in this case is 5A. Set my channels again, and this has to go to 2 and 5. It changed between last night and this morning. Don't capture anything. I'm doing stereo right now, and then I'm going to pull up my widgets of just 3 controls. You have to have all of these controls. So what am I doing in here, though? I'm adding, I didn't add this, and this is an LFM1, LFM2. That should have been added in here. When I originally wrote this and went to the Python conference, scientific Python conference, one of my reviewers said, you have to use those global variables. It might not always work, but you see it worked. The global in the notebook made it inside the callback somehow or another, but technically you should, if LFM1 is defined out here, and I want to use it inside this callback, everything inside this callback has local scope, as it's called in programming. If I want to get access to a variable that's outside the scope of that function, I should have to bring it in with a global. Everybody know what I'm talking about with global variables? Python seems to be very nebulous on that, but I just added that in. So what I'm doing down here, though, is I'm saying for playback, I'm not going to use the input data. You're not going to use the input data in any of the examples that you're doing here. You're always going to be using generated data. So the input never gets used. But here what I need to do is I need to make my slider change the period in LFM1. And then what I need to do is I need to call LFM1 to generate a sequence of phase values and take the cosine of them so they'll become a waveform, copy those into channel 0, and then I'll just copy those into channel 1. You're going to be doing it for two different LFMs, LFM1 and LFM2. So I'm showing this right now in the video because it'll be captured, it'll be archived, you'll be able to go back and look at it. So I'm giving you some nice helps right now. So let me run that. So now I have chirp rate in here and the same two sliders. It's annoying, I know. My wife doesn't like any of this stuff whenever she hears me doing it, but imagine a radar or a sonar. I mean, you might be chirping in order to get a return off of that. So the motivation for this was not listening to it and being amused by it. It was how it would be used in a real application, a chirping application, where you're trying to do something. And I worked with bat signals from the zoo many years ago on a capstone project, and bats do chirp. I have the captures that we made down at the zoo, and they obviously echolocate too, because they found the fruit that was hanging in the bat cave, and we got a really interesting set of chirps captured when a whole bunch of bats were trying to get on the same piece of cantaloupe, and they were all being picked up on the microphone, ultrasound, but then we translated it down in frequency so you could listen to it. That was a fun project. I got on TV too. Not me, my hand, doing something with the playback, but the students, it was a really good project. It was a true interdisciplinary project because it was for a kiosk that they had at the zoo for a while. Other things that are in here, like this one, I have a complete sample code. This is the exact same filter, though, that shows up in Lab 5 for those of you in the lab class. So here you can see how I define a filter. I define some sliders here, and then I can see how the bandpass filter is set up, and I can plot the bandpass filter. But what you do in this project, in the lab, you're going to code this in C, and you're going to be able to adjust the bandwidth of that bandpass filter and the center frequency and do it in real time. Here, it's just an example that's built in here to get you motivated for the real part of this problem. So here's the callback function for that, and I'm taking advantage of some functionality from SS, the SIG-SYS module. And again, I'm just playing back. In this case, I have a speech waveform that's going to get played back over and over again. And then I'm going to add, then down inside of here, I add noise to it, and I can change the signal to noise ratio. So let's run that cell, and then I have to remember this needs to go to 2 and 5, and so I have just gain. This is a mono application, and I can set signal to noise ratio. It's not working. Oh. That's probably the channel that's not working on my cable. I didn't try this beforehand. I thought I'd be risky and try something that maybe wasn't going to work. Well, try this on your own. It's already built up in there. You should hear speech, and then you should hear noise. And what you get to do with this, I didn't get any error messages, so that's suspicious to me. But what you get to do is listen to the speech, and you can control where you set the pass band and the width of the pass band. And the idea is by tuning the center frequency, the bandpass filter, it's a male voice, you can tune it so that you can reject the noise and hear better in the face of an increasing amount of noise. And it's an interesting acoustical experiment, like how does your ear hear it? you want to just hear the full bandwidth, in which case then you make this really wide. And where do you want to center this? I find it's best to make it lower and then close this up so that I can reject more noise outside of this, the male voice. It's just a kind of a cool thing. When you do this in the lab, you're going to test it probably just with a noise generator, just to prove that you can see this thing moving around on the network analyzer. It'll move around as you change the slider controls. Okay, I could keep running on this, but I've got to stop. So I don't know why that's not working, but it's not a major deal. It's more fun to play with on your own. That way you can explore hearing stuff. So now what I want to go to is what I have in here in this chapter 4 notebook, which is probability, random variables, and random sequences. So here, if you're not content with what NumPy has for stats, I just want to sort of blow your mind away with what SciPy stats has got in it. This is a full, very comprehensive statistical signal statistics package, and there's a lot of stuff in here. I don't know what it is. You can find out about it on scipy.stats, which the signal package is the one we use quite a bit. I'm happy for here just using what's already available, and since I've imported the entire NumPy, I have access to things. So here I've created using RAND, and if I go to the RAND sub-package within NumPy, you can see you can generate a lot of different types of random variates. I'm really only care about the two that you're familiar with from your 2610 era, and that would be RAND-N and RAND. Sometimes I like to use RAND-Int, but RAND and RAND-N is what I'm using here. So I'm creating some random numbers, and RAND is uniform on what interval? This is a test of your knowledge from a previous class. When you run RAND in most all programming languages, what does it generate? Generates 0 to 1, absolutely right. So here I've shifted it, so it's going to be -1/2 to +1/2. Here I'm taking it as is, and here I've scaled it by 5, so it's going to go 0 to 5, and then it's going to be shifted up. I have this in here because this relates to a problem on the next homework assignment where you're going to do this. So create those 3. Then I can create histograms with the hist function, which is part of matplotlib, but that's been imported into the workspace. So you can see what the options are for there. I personally like and want you to use density equals true, so that way it will scale the histogram to be like a PDF. It'll be probability density, and then the number of bins, and then x2. So that's uniform on 3 to 8. That's what we did in x2. If I want to compute the variance of x1, which was the random uniform from -1/2 to +1/2, I compute variance, and then as the second value here, that's delta squared, which is 1, right? For uniform on 0 to 1, delta is 1 divided by 12, and that's how many samples did I put in here? 100,000. So that's measured, theoretical. If I want to now look at the covariance between random signals x1 and x2, which are generated from independent calls, I can do that by just doing covariance, and what do I get here? These are multiple values of variance. This is the variance of x1, and along the diagonal is the variance of x2. But the covariances are along the off diagonals of this matrix, and those are essentially 0. I mean, 10 to the minus 4 is as good as you're going to get with a random number generator and 100,000 samples. Does that make sense? Cove is getting several quantities. If you wanted to use it in another way, you'd have to read about it in its help. But you could do other things too. I don't think you can't get a covariance between two random vectors unless you use covariance, though. You could parcel it out if you wanted to. Python lets you do something like this, so you could do if you wanted to get the first entry, you could do something like that. This would be the very first entry in the matrix. And unlike MATLAB or Julia, it seems weird to have the first element in a matrix be at index 0, 0, but that's the way Python works. Okay, so this is just the stack up of the PDFs, and what I did here was I took x1, put up its PDF, put up x2, which was the 3 to 8, and then I decided to add all three of them together. And you learn in random variable theory that if you take independent random variables and add them together, the PDF is going to be the result is going to be the convolutions of the underlying PDFs. So that's what I have going on right here. If I was to just simplify this and put in x1, let's say, what should I get? I'm convolving a rectangle PDF with a rectangle, and I'm going to get a triangle, right? Except I don't have the right range on here. Oh, wait a minute, I can't do that because they're correlated with each other. I have to pick a different one. So I'll pick x2, that was uniform. But the widths of these two are not the same, so I get a trapezoid. Okay, maybe I screwed up. Maybe I should have made another one. This also you do on set number 5. I'll call it 1A. And I can go down here and do 1A in here. Now I get a triangle. And so it starts out as a rectangle from -1/2 to +1/2, and you convolve, the width expands, right? So it goes -1 to +1. Then I have some other experiments in here where I created two different types of random variables for an experiment that tracks the notes. This is 10,000 samples. One is going to be uniform, the other is going to be Gaussian. So uniform and Gaussian. They've been created in such a way, though, or I'm going to scale them in such a way that their variances are equal. Well, I guess I didn't do that in this example. So there's the variances. They're not equal. The normal one has got a variance of approximately 1, and this has got the 1/12th in it. But then I proceed to do experiments where I'm going to cross-correlate before and after filtering, and that is talked about in here. I'm running rapidly out of time, so I'm going to stop there. And I'm going to go back to the notes here in a second. I'm going to see if there's anything I want to talk about. Quantization, nope, we didn't make it there yet, so we're not quite there yet. But that example is backed up by this in here where I wanted to get the autocorrelation function at the output of a first-order low-pass filter. So if I want to get the autocorrelation on Y, I have to use what was just talked about before we took the break, and that is I have to go after this CL function, and then I'm going to be convolving it with white noise, which will be a delta, but I have to inherently get that. So down below here, I go after that. You have a homework problem that has you do this, but you get to tap into this example and just make it work. So here, I switch to the Z domain. So I want to get this convolution done, h of L times h of minus L, and I switch to the Z domain, and I have to remember what is the region of convergence on h of 1 over Z. This was, when I talk about that theorem, I generally talk about the idea of wearing a sock, where the tube of the sock, the region of convergence would say be the exterior of that, looking at the cross section of your sock. If you turn it inside out, the region of convergence becomes now the inside of that. That's my weird analogy. If you don't like that, just look at the math involved with it. But it's like turning something inside out. And I think about if your socks are on backwards, it's because they got turned inside out, right? You have to flip them around before you put them on. At any rate, though, that's the region of convergence. So you've got these two terms in here, h of z and h of 1 over z. You've got a scale factor that comes out of this when you do the normalization in here. And then you inverse Z transform that using partial fraction expansion, solve for the coefficients, and what we get for this convolution then of h of L and h of minus L, or h of m and minus m, we get a double-sided exponential, which you actually saw in a homework problem a while ago. So theoretically, the autocorrelation function of white noise going through a first-order low-pass filter should be a two-sided exponential. And that's what I show here, and pretty sure that's what I showed in here. If I can get on to where I do it, and I may not be able to get this right. Okay, here we go, it's right here. Normal samples x1, x2, and then I'm going to process x1 through this filter. Then down here, I should be doing a plot of rx1, 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 rx2, rx1, y1. Okay. I forgot to load digital com package here. Okay, as expected, this is the autocorrelation function of the white Gaussian or white normal noise with itself. It's a delta function, height being 1. This is when I take the Gaussian, vary at x1 and correlate it with x2, which is uncorrelated, I get 0. This is what happens when I correlate x1 with y1, which comes out of the filter. I get this single-sided exponential. And now if I go ahead and just flip this around and go y1 with itself, now it should be the two-sided exponential, which it is. So that's the measured version of this in Python. Then, of course, I do the frequency response of the filter, so that's our RC-like low-pass filter, and that's how it correlates the noise. As a result of going through the filter, it now becomes correlated. Why? Because the filter has memory, so it gets correlated as a result of going through a memory-type device. I'm kind of getting a little bit wrung out here. What should I be telling you that's going to happen next? After all these examples, we start modeling a few other things. So we're going to go ahead and start modeling the sample and hold, more detailed model of the A to D, more detailed model of the D to A, and then finally a realistic reconstruction filter. Maybe it's compensated, and also in the process look at a more realistic anti-aliasing filter. I'm bloated in this part of the notes. I can't possibly go through everything, so I'm going to have to hit the high points of that. At the very end of all of this, which I'm going to have a hard time getting to, but which I want to spend a bit of time on. We're also going to talk about sigma delta, oversampling and noise shaping. And this is how we can approach getting a 1-bit A to D converter. And the amazing feat of that will be, if I can get to the block diagram here, will be this block diagram. And this is kind of what you already did some analysis on the last homework set. Except this is mixed signal. So this is switch capacitor integrator, which gets replaced in the model with a discrete integrator, and that's what you did. I don't know if you remember, you had a 1 over 1 minus c to the minus 1 in part B of that homework problem. Remember you did the feedback stuff? This is that model right there that you already played with. You have the quantizer and then the feedback path. And this is the road that I'll try to talk a little bit about of how you can make the quantizer here be just 1 bit. It's pretty amazing how you can do that with oversampling and the noise shaping. We're out of time. I want you to at least know about sigma delta converters because they are everywhere, but not in software-defined radio that much. There is a bandpass sigma delta that Analog Devices has for RF, but in audio they dominate the marketplace pretty much. So, any questions as we're blasting off? I'm going to spend some time in lab today, but because my wife had this procedure done, heart procedure done, she needs to have somebody, and my son, I made him stay home from work today so I could come here, and I need to swap out with him. And honestly speaking, my mother-in-law moved in about a week and a half ago, and she's about to turn 90, so we've now got 2 people in the house that need caregiving because my wife was the caregiver for her. And a puppy on top of that. A little bit crazy. Okay, I'm signing off.